Zeal Education Society, redefining excellence.
Welcome back. In the previous lecture, we have seen what is state transition matrix, how it is related to solution of homogeneous state equation, and then Laplace transform approach to compute the state transition matrix. Let us make one small correction in the earlier lecture, problem number 2. The matrix A was minus 1, 1, 0, minus 1. So this shall be minus 1. Everything else is correct. And now in today's class, we will see another approach to determine the state transition matrix, and that approach is the combination of Caley Hamilton theorem and Sylvester interpolation formula. So as we know that every matrix A, say as per Caley Hamilton theorem, every matrix A satisfies its own characteristic equation. And what is that characteristic equation? That characteristic equation is given by lambda I minus A. If we expand this is lambda raised to n plus A1 lambda raised to n minus 1, so on up to a n minus 1 lambda plus a n equal to 0. And then as per Caley Hamilton theorem, it employs that a raised to n plus a1 a raised to n minus 1, so on up to a n minus 1 a plus a n I, this is also equal to 0. Now we will extend this concept to some concept of minimal polynomial. So if, let us consider a polynomial having a as its root is called as minimal polynomial of A, and that will be of order m, and that is given as, say, phi lambda is that polynomial, and that is given by, say, lambda raised to m plus a1 lambda raised to m minus 1 plus so on a n minus 1 lambda a m minus 1 plus a m equal to, not equal to 0. This is not equal to 0, such that m is less than equal to n. This will be equal to 0 if m is equal to n, otherwise it will not be. And then polynomial for a, now a is root of it, so for a it will be a raised to m plus a1 a raised to m minus 1 a m minus 1 a plus a m I, this will be equal to 0 because a is its root, and this particular polynomial is called as the minimal polynomial of matrix A. And then using Sylvester interpolation formula, we get a set of equations represented by the determinant and let us consider there are two cases in this case. The first case is case 1. A has distinct eigenvalues, and in this case this determinant is given by 1 lambda 1 lambda 1 square so on lambda 1 raised to m minus 1 e raised to lambda 1 t. This is the first row, and same is repeated for the next lambda 2 square lambda 2 raised to m minus 1 e raised to lambda 2 t, and the same will move up to lambda m because it is the m degree polynomial. No doubt m can be equal to n. In many cases you will get m equal to n. Lambda m square lambda m raised to m minus 1 e raised to lambda m t. This is in continuation, and finally the same is obeyed by matrix A. So a square a raised to m minus 1 e raised to at, and this is equal to 0. So this is the determinant. Now if you look at these are the m different eigenvalues followed by the matrix A. So this determinant is m by 1 into m by 1, and what happens by this, we get different equations. So solution of this can be, or this can be represented by the set of equations like, say for example, this will be every one up to this will be multiplied by some constants. So it is alpha 0 multiplied to this plus alpha 1 lambda 1 plus alpha 2 lambda 1 square so on up to plus alpha m minus 1 lambda 1 raised to m minus 1. This will be equal to e raised to lambda 1 t. Now we have the value of lambda. So unknowns are alpha 0 to alpha m minus 1. There are m unknowns. So if we want to solve these, we must have m equations. So how to get m equations? 1, 2, 3 and so on, 1 to m. We will get m equations. Like say for example, again multiply the same constants, alpha 0 plus alpha 1, now lambda 2 plus alpha 2 lambda 2 square so on up to alpha m minus 1 lambda 2 raised to m minus 1, and this is equal to e raised to lambda 2 t. And if we go on continuing the same, for the last one we will get alpha 0 plus alpha 1 lambda m plus alpha 2 lambda m square alpha m minus 1 lambda m raised to m minus 1. This will be equal to e raised to lambda m t. And by solving above m equations, we get alpha 0, alpha 1 up to alpha m. So these are known, and now apply the same to the last equation, correct? So what we get, if we apply the same to last one, we get alpha 0 I, because this is a matrix, this was the vector, or this was the eigenvalue number, this is a matrix, so alpha 0 I plus alpha 1 A plus alpha 2 A square, so on up to alpha m minus 1 a raised to m minus 1, this will be equal to e raised to at. So what will be the steps to solve the problem, to find out the state transition matrix? This is the formula, but this formula involves the coefficients alpha 0 to alpha m minus 1. This we have to determine, and so the steps will be, first we have to form the determinant that requires the values of lambda, and that means we have to find out the eigenvalues, step number 1. Then for that get this determinant by Sylvester interpolation formula and get the equation systems and solve for the unknowns and put it here, you will get e raised to at. But this was for the distinct roots. Now what if there are repeated roots? Let us consider only two repeated roots are there, lambda 1, lambda 1. So lambda 1 is with multiplicity 2 and remaining roots are distinct. So if we do here 1, lambda 1 square, lambda 1 raised to m minus 1, e raised to lambda 1 t, and if we repeat the same, then the two equations will be same, and then you cannot solve. You will not have the linearly independent solutions. The solutions cannot be obtained. It will be non-trivial solution. So then in that case what we have to do, the second row will be this one for the distinct eigenvalue, and then for the repeated root we have to take derivative of this with respect to lambda. Let us see it. Let us see the case 2. So case 2 is repeated roots, repeated eigenvalues. Repeated eigenvalues, and what we will consider, we will not enter into much complication, but what we will do it for eigenvalues are, say eigenvalues, two repeated, only lambda 1 is repeated. Lambda 1 has multiplicity of 2, and the same can be extended for 3, 4 and all m. There is no issue. So in that case, the determinant will be so what we will do, first this one we will write the same type, say 1 lambda 1 square, so on up to lambda 1 raised to m minus 1, and then e raised to lambda 1 t. This is the distinct one, repeated we have to consider, and then for the repeated, differentiate this entire row with respect to lambda 1. So this will be 0, this will be 1, this will be 2 lambda 1, so on. This will be m minus 1 into lambda 1 raised to m minus 2, and this will be t e raised to lambda 1 t. We are not differentiating it with respect to t, we are differentiating it with respect to lambda 1, and the remaining are same. So this will be 1. Now lambda 1, next will be lambda 3, lambda 3 square, lambda 3 raised to m minus 1, e raised to lambda 3 t, proceeding further up to lambda m, lambda m square, lambda m raised to m minus 1, e raised to lambda m t, and this is equal to 0. So this is in continuation. And then the equations formed will be now here alpha 0 into 0. So this will be, first equation will be alpha 1 into 1 plus 2 alpha 2 into lambda 1, so on up to m minus 1 alpha m minus 1 lambda 1 raised to m minus 2, and that will be equal to t e raised to lambda 1 t. The first equation is only different. The remaining equations are same. Say this will be, the next equation will be, for this one it will be alpha 0 plus alpha 1 into lambda 1 plus alpha 2 into lambda 1 square, so on up to plus alpha m minus 1 lambda raised to m minus 1, and this will be equal to e raised to lambda 1 t. And then the next equations will be, for this one alpha 0 plus alpha 1 lambda 3 plus alpha 2 lambda 3 square plus alpha m minus 1 lambda m raised to m minus 1, even this shall be lambda 3, this is for lambda 3, and this will be equal to e raised to lambda 3t. And finally the last one will be alpha 0 plus alpha 1 lambda m plus alpha 2 lambda m square plus alpha m minus 1 lambda m raised to m minus 1, and this will be e raised to lambda mt. Again there are m equations. So these are the two for the two repeated roots and remaining. So solve these m equations. So these are the m equations. So solve m equations to get alpha 0, alpha 1, so on up to alpha m minus 1. Then e raised to at will be equal to alpha 0 I plus alpha 1 a alpha m minus 1 raised to a m minus 1. The formula is same. And what we will do, typically for distinct roots and repeated roots, a 2 by 2 case, we will do it. Say for 2 by 2 A matrix with distinct roots. We will write only the determinants. It will be 1 lambda 1 e raised to lambda 1 t, 1 lambda 2 e raised to lambda 2 t I a e raised to at, and this is equal to 0. Even here we have to write that last one, I a square a raised to m minus 1, and this is e raised to at. This is the determinant which is forming these m rows, are forming these m equations to solve these coefficients, solve for these coefficients and get the e raised to at from the last row. Now if we have two by two A matrix with repeated roots. Roots are repeated, and then For the distinct one, 1 lambda 1 e raised to lambda 1 t, this will be I a e raised to a t, and the first row will be derivative of this with respect to lambda 1. So 0 1 t e raised to lambda 1 t. And what are the equations formed from this? Here the equations are alpha 0 plus alpha 1 lambda 1 is equal to e raised to lambda 1 t, and second one is alpha 0 plus alpha 1 lambda 2 is equal to e raised to lambda 2 t. Solve the two equations, get alpha 0 alpha 1 and put it in the last one. Last one is what? Alpha 0 I plus alpha 1 a is equal to e raised to a t. And same way we can form for this as well. This will be alpha 0 0 plus alpha 1. So alpha 1 is equal to t e raised to lambda 1 t. Then alpha 0 plus alpha 1 lambda 1 is equal to e raised to lambda 1 t. Solve for these two, get alpha 0 alpha 1 and then find out alpha 0 I plus alpha 1 a is equal to e raised to a t. Done. Same can be extended for 3 by 3. This will be 1 lambda 1 square, and the same. This can be extracted here. Now what we will do? We will solve the same two examples and verify the answers. Are we getting the same? We shall obviously we shall get the same. So example number 1 is determine STM, state transition matrix of A is equal to, the matrix was 0 1 minus 2 minus 3, and which approach? By Caley Hamilton Sylvester interpolation approach. Solution. So first step, we have A is equal to 0 1 minus 2 minus 3. So first step is to find out the eigen values. Characteristic equation of A is lambda minus a equal to 0, so it is lambda minus 1 2 lambda plus 3 equal to lambda square plus 3 lambda plus 2 equal to 0. So the eigen values are lambda equal to minus 1 minus 2, and they are distinct. Then determinant forming set of equations, which equations from the minimal polynomial using Sylvester interpolation formula is, this determinant will be, they are the distinct roots, two values are there, so 1 lambda 1 e raised to lambda 1 t, 1 lambda 2 e raised to lambda 2 t, and then I a e raised to a t, and this will be equal to 0. And now this is forming the equations. So alpha 0 plus alpha 1 lambda 1 is equal to e raised to lambda 1 t. Second equation, alpha 0 plus alpha 1 lambda 2 is equal to e raised to lambda 2 t, and this is giving me alpha 0 lambda 1 is minus 1, so minus alpha 1 is equal to e raised to minus t, first equation. And second equation is alpha 0 minus lambda 2 is minus 2, So minus 2 alpha 2 is equal to e raised to minus 2t. And let me call this as 1 and this as 2. So by 1 minus 2 we get 1 minus 2. So alpha 0 gets cancelled. Alpha minus alpha 1 plus 2 alpha 2. So I get here, sorry, this is alpha 1. So I get, so upon subtracting I get alpha 1 is equal to e raised to minus t minus e raised to minus 2t. One coefficient is obtained, and then put it in equation 1. So from 1, what is alpha 0? Alpha 0 is e raised to minus t plus alpha 1. So it is e raised to minus t plus e raised to minus t minus e raised to minus 2t, and that is equal to 2 e raised to minus t minus e raised to minus 2t. So this is alpha 0 and alpha 1 are obtained, and then we have e raised to at is equal to alpha 0 I plus alpha 1 a. Alpha 0, alpha 1 are the scalars, and they will be multiplying every element of matrix I and a. So then this will be alpha 0 into I. So I is 1 0 0 1. So it will be alpha 0 0 0 alpha 0. So what is alpha 0? Alpha 0 is 2 e raised to minus t minus e raised to minus 2t 0 0, and this will be 2 e raised to minus t minus e raised to minus 2t, and plus what we have to add here, plus alpha 1 into a. So what is the a matrix is here? So every element in a will be multiplied with alpha 1. This is alpha 1. So this will be 0, then 1 will be multiplied with this. So e raised to minus t minus e raised to minus 2t. Then this will be minus 2. So minus 2 e raised to minus t plus 2 e raised to minus 2t, and the last element is minus 3. So minus 3 e raised to minus t plus 3 e raised to minus 2t. And now do the addition element by element. This plus 0 is 2 e raised to minus t minus e raised to minus 2t. Then 0 plus this is e raised to minus t minus e raised to minus 2t. Then 0 plus this is minus 2 e raised to minus t plus 2 e raised to minus 2t. And last one, this 2 e raised to minus t minus 3 e raised to minus t is minus e raised to minus t plus 2 e raised to minus 2t. So which is same as the earlier. And this is another method. Let us solve the second example also by the same method. So the second example was example 2. Determine state transition matrix of A is equal to, it was minus 1 1 0 minus 1, and let us start solving it. We will solve it very quickly. Here we have A is equal to minus 1 1 0 minus 1, then its characteristic equation is lambda minus a. So this will be lambda plus 1 minus 1 0 lambda plus 1. So that is equal to lambda plus 1 square equal to 0. So lambda equal to minus 1 minus 1. So it's repeated root case. Then the determinant will be this will be 1 lambda 1 e raised to lambda 1 t I a e raised to a t, and the first term will be derivative of this will be 0, derivative of this will be 1, and derivative of this with respect to lambda 1 will be t e raised to lambda 1 t, and this gives me the solution alpha 0 into 0 alpha 1 equal to t e raised to lambda 1 t, and alpha 0 plus alpha 1 lambda 1 gives me e raised to lambda 1 t, and these two sets are equations are giving me alpha 1 equal to t e raised to lambda 1 is minus 1, so t e raised to minus t, and alpha 0 minus alpha 1, this one is equal to e raised to minus t, and this gives me, so alpha 1 is already obtained, alpha 0 will be equal to t e raised to minus t plus e raised to minus t. So both are obtained, and then e raised to at will be equal to alpha 0 I plus alpha 1 a, and that is equal to, what is alpha 0? This one is alpha 0, t e raised to minus t plus e raised to minus t 0 0 t e raised to minus t plus e raised to minus t plus alpha 1 a. So what is a? Minus 1 1 0 minus 1. So this will be minus t e raised to minus t multiplied with 1, it will be t e raised to minus t, again multiplied with 0 it will be 0, and this will be minus t e raised to minus t, and now add the two. This term plus this term, t e raised to minus t gets cancelled, this is e raised to minus t, 0 plus t e raised to minus t is t e raised to minus t, then this will be 0 plus 0 will be 0, and here this again this gets cancelled, it is e raised to minus t. So we have got the same answer. So in this lecture we have seen the second approach to find out the state transition matrix. In the next lecture we will see another method. Thank you.